powerful than nuclear weapons. Perhaps a substance that, in just a microscopic quantity, could cause unimaginable destruction. The destructive potential of antimatter is simply incredible. Only half a gram of antimatter would be enough to create a bomb, such as the one that destroyed Hiroshima. And 1.5 kilograms of antimatter would break the record set by the thermonuclear Tsar Bomba tested on Novaya Zemlya Island in 1961. Such a substance with fantastic...
What danger does it pose, and what is its importance to all of humanity?
In 1928, the British physicist Paul Dirac suspected the presence of antiparticles with an opposite electric charge. After 5 years, Dirac received the Nobel Prize for his prediction. The first antiparticle was discovered by American physicist Carl Anderson in 1932. Thus, humanity recognized the positron, a positively charged copy of the electron. This mysterious mirror reflection of matter excites the minds of humanity with its capabilities. If antimatter collides with particles of the right matter, they completely annihilate each other. That is, they cancel each other out while emitting powerful radiation. Oxford University professor Frank Close, specializing in particle physics, wrote in his book Antimatter that the annihilation of a kilogram of antimatter will produce about 10 billion times more energy than the explosion of 1 kilogram of TNT. Substance reactions from antimatter are 1,000 times more powerful than the nuclear fission of uranium in nuclear power plants. But what does this mean in practice? The nuclear explosion in the Japanese city of Hiroshima had a capacity of approximately 13 to 18 kilotons of TNT. The death toll there was approximately 70 to 80,000 people. An explosion of such force leads to complete devastation in a radius of about 1.5 kilometers, and less than half a gram of antimatter would be enough to reproduce it. Later, the number of victims of this Japanese tragedy increased to 140,000 due to the effects of radiation sickness. But unlike traditional nuclear explosions, after the explosion of a bomb from antimatter, there will be no residual radiation. Calculations show that in an explosion with a capacity of 100 megatons, the zone of absolute destruction will extend 35 kilometers from the epicenter, and the zone of severe destruction will cover a radius of up to 50 kilometers. Such a force can destroy any of the largest cities on our planet. And for this, you need only a few kilograms of antimatter. Exactly 100 megatons was the design capacity of the Tsar Bomba, which was tested in a lighter version that was almost half of this. But even the weakened version of the bomb is terrifying. The measured power of the explosion was equal to 58.6 megatons of TNT. Such energy can be released during the interaction of about 1.5 kilograms of antimatter and 1.5 kilograms of substance. Witnesses felt the blow and were able to describe the explosion thousands of kilometers from its center. Radiation, even at a distance of up to 100 kilometers, led to third-degree burns. The blast wave circled the globe 3 times. The first time in 36 hours and 27 minutes. But what happens if you blow up 10 kilograms of antimatter? About the same as on December 26, 2004, the Indian Ocean earthquake, the epicenter of which was located off the northwestern coast of Sumatra in Indonesia, caused the deadliest tsunami in modern history. The magnitude of the earthquake was about 9.2. The movement of lithospheric plates created waves with a height of more than 15 meters. The tsunami reached the shores of Indonesia, Sri Lanka, southern India, Thailand, and many other countries. According to various estimates, 225 to 300,000 people died. Many people were carried away by the receding water into the ocean. The exact number of dead and missing remains unknown to this day. The shock wave from this earthquake passed through the entire planet. The islands located near the epicenter shifted tens of meters. According to theoretical models, the mass shift and huge energy release, equivalent to 480 megatons of TNT, slowed the Earth's rotational speed slightly, reducing the length of our day by about 2.68 microseconds. A similar force can be expected from an explosion of only 10 kilograms of antimatter. This energy is enough to boil 150 liters of water for every person on Earth. Mankind remembers another natural disaster that befell Indonesia in 1815. The eruption of the Tambora volcano on the island of Sumbawa was the most powerful in recent centuries. For 3 days, the area within a radius of 500 kilometers from the volcano was hidden from the sun by huge masses of volcanic ash, which subsequently spread more than 1,000 kilometers from the eruption site, causing serious changes to the planet's climate. Global cooling was experienced by the entire northern hemisphere. The year 1816 was nicknamed the year without a summer. The total eruption energy is estimated at 20 gigatons in terms of TNT. The same amount of energy would be released during the explosion of a bomb from antimatter weighing just 500 kilograms. So, you want to see the apocalypse? Then detonate 2.5 kilotons of antimatter. An energy release of 100,000 gigatons of TNT would trigger the onset of a new ice age. This already happened on Earth 65 million years ago, when an asteroid larger than Mount Everest fell on the Mexican peninsula called Yucatan. Hot debris soared high into the atmosphere and beyond. Falling back, this debris heated the air to the temperature of the inside of an oven. A large amount of dust fell into the atmosphere, which for several years blocked the Earth's surface from the sun. An almost nuclear winter had arrived. Most scientists believe that this event caused the death of the dinosaurs. Fortunately, the creation of an antimatter bomb is only theoretic. In practice, obtaining antiparticles is a very time-consuming, complex, and expensive undertaking. The European Center for Nuclear Research, or CERN, uses the Large Hadron Collider, a charged particle accelerator, to create and study antiprotons. CERN employee physicist Ralph Landua assures that the low efficiency of the process of obtaining antimatter is the key to safety and the inability in the near future to create serious weapons based on it. According to Landua, the synthesis of 1 gram of antimatter with current technology would cost about $1,000 trillion. For comparison, the annual U.S. budget would be enough to create only a few micrograms of antimatter. But it's not enough to simply create antimatter. You still need to preserve it, because if it comes into contact with normal matter, it will be instantly destroyed. It will disappear. To prevent this suicide, scientists have invented traps from a very strong and complex magnetic field configuration. To date, the best result that has been achieved is the preservation of antimatter for about 1,000 seconds. And yet, the creation of weapons that can shoot antimatter is no longer fiction. Physicists from the University of Michigan, under the leadership of one Karl Kruszelnik, designed an ultra-compact accelerator, a gun that can fit on a regular table. Compared to the Large Hadron Collider, this thing looks almost like a toy. It operates on the basis of particle acceleration techniques discovered by American scientists in the early 1980s. A laser beam passing through a jet of helium forms a stream of electrons, and a thin metal foil blocks their way. When electrons collide with the foil, positrons are formed in the flow. Next, a magnet comes into play and spreads positrons and electrons in different directions. Antimatter is also an ideal, super efficient fuel. An antimatter engine would be the most efficient ever created, because 100% of the mass of the substance and antimatter is converted to energy. About 10 grams of antiprotons would be enough to deliver a manned spacecraft to Mars in just 1 month. Today, for an unmanned ship to reach Mars, it takes almost a year. The only obstacle to the creation of mega-powerful weapons or fuel is the inability to synthesize antimatter in large volumes. For all the time spent on these efforts, people have only created an insignificant and small dose, 19 nanograms of antiparticles. This is barely enough to boil a cup of coffee. But what if we learned to capture antimatter from space? Then an antimatter bomb will become reality in the near future. What are the consequences of such technology in the hands of, let's say, criminals? Is it possible to prevent the creation of such a weapon, or are we doomed? Will antimatter someday destroy our civilization or become the strongest energy catalyst for its development? If you liked the video, give it a thumbs up. Don't forget to subscribe to the channel if you haven't done so already. Click the bell to receive timely notifications of new, interesting videos that are waiting for you ahead.